Okay, so today we will continue our topic on the constraint optimization. And today we are going to look at the simplex method. So earlier we uh, looked at the formulation of the linear programming approach, and we also set up the graphical method. So we have seen that in the graphical method, we set up an area bounded by the constraints, okay, bounded by the constraints, and depending on these constraints, we can then find the optimized solution. And then we also found that the optimized solution is found at the corners of the shape, which is resulted. So for example, here in the case of this graphical solution, the optimized solution is at this point C. And how do we determine that this is this point which is giving us the optimized solution? It is because that curve which is for the objective function, that objective function curve is only intersecting this boundary of this feasible region at only one point. If we move this curve in, then it will be intersecting that feasible region at more than 1 points, okay? But only at this point it is touching upon at 1 point only. So that is the feasible solution. That is the optimum solution for this linear programming problem. So depending on the how we are looking at the how we are setting up the constraints, we can have the unique solution, we can have the alternate solutions, we may not have no feasible solutions, and we may have the unbounded problem. So this is the example for the alternative optima. That means we can have the optimum value at more than 1 point. Okay. With no feasible solution in that situation, the constraints are such that there is no feasible area. So if there is no feasible area, then there is no feasible solution. And in the unbounded results, the values are the constraints are such that, and on one side there is no boundary, okay, on one side of that. So for example, over here there is no boundary. So if we will move the solution into that direction, there will be a constant increase in the value of z, in the value of the optimum function, and there will be unbounded results. So alternative optima occurs when the objective function line, then the objective function line is parallel to one of the surfaces, one of the edges. So for example, this is one edge, this is another edge, and this is another edge, okay, is parallel to one of these edges, okay. Then we can have the alternative optima. That means on any point on those edges, there will be a solution, okay. The solution can be at this point, can be at this point, can be at this point. So all of those solutions will be giving us the equal results. Okay, so these are the alternative optima. And then so that was the graphical approach. So the purely mathematical approach is this, which is the simplex method. So this simplex method assumes that the optimal solution will be at an extreme point, or the corner, at the extreme corner. Okay, so just like in the case of this graphical approach, we have seen that for this for the graphical approach, we have seen that over here, the solution was available at this point, which was the point which is one of the corner, which is one of the corner point of this bounded area. The approach must discern whether during problem solution an extreme point occurs. And to do this, the constraint equations are reformulated as equalities by introducing slack variables. So in this method, this is the mathematical method. In the mathematical method, we try to employ the equations. So, but in the linear programming solution, instead of equations, we have equalities. So to convert an to convert an inequality with the equation, we need to introduce some variables, extra variables. We call them as the slack variables. And then that inequality becomes equal to the equation. So it is converted, inequality is converted into the equation. So for example, if 7x1 plus 11x2 is less than or equal to 7, which was one of the constraint in our previous problem, if we introduce a slack variable s1, then the slack variable is such that when it is added to 7x1 plus 11x2, it becomes equal to 77. So in this case, that inequality is converted into an equation. So a slack variable measures how much of a constraint resource is available. So for example, for this, if we define a slack variable S1 as the amount of raw gas that is not used for a particular production level, X1, X2, and add it to the left side of the constraint, it makes the relationship as exact. Okay. So if slack variable is positive, it means that we have some slack, that is, we have some surplus that is not being used. If it is negative, then it tells us that we have exceeded the constraint, so which is not possible. So which means that we can only look at the slack values which are positive values, or in case if it is 0, if we are exactly meeting the constraint. So the value of this slack variable, which we will be using in this method, will be either 0 or a positive value, either 0 or a greater than 0 value. So similar slacks we can introduce into all the constraints. So we can name them as S1, S2, S3, and S4. So remember that the gas problem was, the example was this, okay? So the following problem is developed from the area of chemical engineering or petrol well engineering. So suppose that a gas producing plant receives a fixed amount of raw gas each week. So we did this problem last week, okay, in the last time. So, and as a result of this problem, we established these set of conditions or the relationships. So in this case, we have to maximize this value of Z, okay, because, and this, the value of Z is equal to 150 x1 plus 150 x2. That means if x1 ton of one type of gas is produced and x2 ton of another gas is produced, we can multiply them respectively by 150 and 175 to get the total profit. So we have to maximize this profit. okay, which is subject to these conditions. And the first condition is about the uh, availability of the gases. So availability of the gases cannot be more than 77. So we implied this situation 7x1 plus 11x2 is equal and plus s1 is equal to 77. So s1 is the slack variable which we introduced to make the inequality into equality. And similarly, the second constraint was the time constraint. So that means the total time which can be spent in this plant per week is 80 hours. So suppose if we spend uh, uh, is 80 hours. So therefore, the condition was 10x1 plus 8x2. That means the gas 1 needs 10 hours per ton. Okay, so total for 10 total time needed will be 10x1, and the second gas needs x2 hours per ton. So total, sorry, 8 hours per ton. So total time needed will be 8x2. So 10x1 plus 8x is equal to, and plus s2 is equal to 80. And similarly, the third and the fourth constraints are the storage constraints. So we cannot store more than 9 ton of x1 and x. We cannot store more than 6 ton of x2. So x1 is less than or equal to 9 and x2 is equal to less than or equal to 6. So for these were 4 constraints. So therefore we introduced 4 slack variables to make those inequalities into equalities. Okay. And then additional constraints are like all the values x1, x2, s1, s2, s3, s4 are greater than or equal to 0. So in this case, then we create a version of the linear programming solution, which is called as the fully augmented version. Okay, so for the solution, then it will see that this simplex method solution is in the looks, it looks similar to the solution of the system of equations, system of linear equations. That means if you can see that we have arranged these equations in a way that it looks like the system of the linear equations. However, there are some differences from the solution of the system of linear equations. So in this simplex method, we will be using the Gauss-Jordan elimination method. Okay, but in addition to the Gauss-Jordan elimination method, there are some further steps as well. Okay, so that we need to understand. So this is some discussion about the number of calculations that will be involved. So which can be determined by this combination of n over m, which is n factorial over m factorial minus n minus m, where m is the number of equations and n are unknowns. So in this case, as we can see that we have how many equations available? We have 1, 2, 3, 4 equations are available for the constraint. Okay, 4 equations are available for the constraints, but the unknown variables are 6, 1, 2, 3, 4, 6. So when we have no more number of variables than the number of constraints, then the solution of the equations has no particular solution. That it can have infinite number of solutions, but subject to some certain constraints, which are over here, and then which there are some more constraints which are hidden over here. We may be able to find the solution. As we can see that this is the same exact problem as we have done with the graphical method. So therefore, it actually has a solution. So although we have formulated it into the equation format where we have 4 equations but 6 unknowns, but some of the uh, uh, relationships are hidden in this case. So simplex method helps us to identify the solution. Okay, so the approach, the graphical depiction of the simplex method is that we will start from, we will take advantage of the observation in which we did in the graphical method was that in the graphical method, we took the observation that the solution exists only at the corners. So there are how many corners? One, A, B, C, D, and E. So if there is any solution of this problem, that solution will exist at the one of these corner points. Okay, A, B, C, D, E. So out of these 5 corner points, A, B, C, D, E, A is obviously not the solution because we want to maximize the this function. So if if the values of x and x2 are 0 or greater than 0, so the minimum value of z is at when x is 0 and when x1 is 0 and when x2 is 0. That will make the value of z as 0 because the value of z will be also greater than or equal to 0. So the minimum value of z is 0. So the value of z is 0 only at when x is equal to 0 and x1 is equal to 0 and x2 is equal to 0. So which is only possible at point A. So at any other point within this feasible region, the value of z will be greater than or equal to 0. So therefore, in this simplex method, then we can start from this 0 point over here. Okay, and then this method will work in such a way that we can move from this point to the next adjacent point. Okay, so we can move either towards this point, this side, or that side. Okay, so we can move from A to E to D to C, and then we will reach the solution. Or we can move from A to B, and then B to C, and then we can reach the solution. So it means that in uh, uh, in this method, in 2 or 3 iterations, we can reach to the solution. So in the first iteration, we will move from A to B. In the second iteration, we will move from B to C. Or if we adopt this method, if we adopt this path A, E, D, and C, so we will need to make the 3 iterations. So from A to E, from E to D, and then from D to C. Okay. So is there any question about this method? Hello?
No questions.
Yeah. So now I'm going to explain this method. So to explain this method, then I will start from this formulation of the simplex method. So we will formulate it like this, maximize this z and subject to these 4 constraints and plus these additional constraints. So we will arrange this the information into the tabular format. So it is called as this tableau. Okay, so although it is a table, we call it as a tableau. So it is called as the simplex tableau. So we will arrange this information into the table into this tabular format, and what you can see that can you visualize that how we have arranged this information? So for example, in this table, we have listed all the variables which we are using. Z is a variable, X1 is a variable, X2 is a variable, and S1, S2, S3, and S4 are variables. So you can see that in this problem, Z, X1, X2, and then S1, S2, S3, and S4. So we have arranged all these variables. So this is these are some of the steps to create the simplex table. And the first row is showing Z, and then next rows are showing the slack variables only, not the x1 and x2 variables, which are the basic variables. Okay, so whereas the slack variables are shown as S1, S2, and S3. So we will skip those X1 and X2. Basically, what we want to find is the values of X1 and X2, which makes this value of Z as maximum subject to these conditions. So slack S1, S2, and S3 and S4 are kind of like uh, not needed answers. Okay, so we are only focusing on x1 and x2 subject to these s1, s2, and s3 slack variables. So we are interested to find the values of x1 and x2, and then here we are putting s1, s2, s3, and s4. But now in this case we are filling the these cells of the table by these values, and then if you can see that this is 1, this is minus 150, this is minus 175, and in the solution there is a solution column as well, or in which we will put this value of 0, 77, 89, and 6. So why it is minus 150 and minus 175? It is because we will take this equation, just remove this word maximize. So if we take this equation, z is equal to 150 x1 plus 150 75 x2. Okay, so we will take 150 x1 and 175 x2 towards the left hand side of the equation. So then it will become z minus 150 minus 175, and then on the right hand side it will be 0. And then there are of course no s1, s2, s3, and s4 in this equation. So therefore, for the place of s1, s2, s3, and s4, we will place 0 over here. On the right hand side it is 0. And then on the left hand side it is 1, which is the coefficient of z, x 100 minus 150, which is coefficient of x1, and minus 175, which is the coefficient of x2. So basically we are writing the coefficients of these equations. Okay, first equation, second, third, fourth, and fifth equation. And similarly we have wrote the coefficients 7, 11, 1, and then 0, 0, 0. Okay, that means 7, 11, 1, and then 0, 0, 0. And then we will start from x1. And for this s1, the second equation, then this is which is for the slack variable s1. So the third equation for the slack variable s2. And in the column of z, we will place 0, 0, 0 over here, and then we will set it up. So now you can understand that for this S2, we have written 10, 8, and 0, because this one is for the slack variable S2. So the values of S1, S2, and S4 will be 0 for this. And similarly, you can see that for S3, it will be for X1, there will be only one value. For X2, there will be only one value. So, and then for S3, it will be S1 or S2 will be 0, S4 will be 0. Only the value of S3 will be 1. As you can see that 1 and 1 for the place of S3. For X2, the value of X1 coefficient is 0, so 1 and then 0. So there are a lot of 0 coefficients in this table, and the values of 9 and 6 over here. So in this way, you will set up the simplex table. So I hope you can get the idea of how to set up the simplex table. So can you set up the simplex table?
Yes.
Okay. So once we set up this simplex table, then we will move to the next step. Okay. So now we will look at this table. Okay. So in the next step, we will look at this table, and then we will look at the first row, which is this Z row. And in this first row, we will have certain negative values. So there are two values, 150 and 175. The most negative value is 175, minus 175. So we will choose this most negative value and the corresponding variable, the corresponding variable with that. So corresponding variable is x2. So we will call this variable as the entering variable. So entering variable is that variable which is the variable in this z row with the most negative value. Okay, entering variable. So this is the first step. Okay, so what will be the meaning of the entering variable? That will be clear in the next step. Okay, so we'll so that's why I have highlighted it, this variable, as the entering variable x2. So next what I will do is I will take I will focus on rows s1 to s4. After I select the entering variable, I will focus in on these rows s1 to s4, and then I will divide the values in this solution column by the respective coefficients in this uh, x2 column, which is the column which we selected for the entering variable. So 77 divided by 11, we will take 80 divided by 8, 9 divided by 0, and 6 divided by 1. So respectively, we will get values of 11, 8, infinity, and 11, 8, infinity, and 1, and 6, right? So we will get the value, no, sorry, 77 divided by 11 is 7. 7, 8, infinity, and 6. Okay, 7, huh? Oh, sorry, 80 divided by 8 is 10, sorry, okay, yeah. So it will be 7, 10, infinity, and 6. So 7, 10, division, because I did this example by the Excel, so it says, it gives the error division by 0. So that is fine, okay. So 7, 10, infinity, and 6, we got these values. So here we can see that out of these 4 values, the what is the least value, least positive value? So what we have to choose is the least positive value, not the negative value. Negative values you will disregard. If there are any negative values, those values you will disregard. We will choose the least positive value. So the least positive value is this 6. Okay, and the 6 is in this 4th row. So now earlier we have selected the entering variable. Now we will select the leaving variable. So leaving variable in this case will be S4, which means that whatever was the entering variable, that will be replaced by the leaving variable. So it means that we will replace in the next step X4 with X2. Okay, so we replace the leaving variable with the entering variable in the previous step. So here I can see that in this step, we have chosen this S4 as the leaving variable, okay, because it is corresponding to the least positive value of this final ratio, which we call as intercept, okay, which we call as the intercept. So in the next step, I think I am showing it like not S4, but X2. Okay, so now in this case, by this process, earlier we have over here S1, S2, S3, and S4, but S4 has been removed from here and it has been replaced by X2. Okay, so this is the only thing which we have done over here. So remember that first we have chosen the least negative value from the first row. That gave us the entering variable. And then we divided the solutions with the coefficients of this columns of the entering variable. And then from those values, we took the least positive value, and the corresponding variable in that row will be the leaving variable. So which was S4, and now S4 has been replaced by X2. Okay, so with this thing in mind, now for this, this was the entering variable column, and then this was the leaving variable row. Okay, so their intersection is at this value. Okay, So this one, this coefficient of 1 now becomes the pivot coefficient. Okay, pivot coefficients. So if it is not 1, okay, then we have to make it as 1. But since now it is already a 1, so then we don't need that step over here. And now here, now the Gauss-Jordan elimination steps are performed. And what are those steps? Those steps will make all the elements in that column except this pivot variable as 0. Okay, so if, for example, if I want to make this one minus 175 as 0, so I will multiply this one by 175 and then add it to minus 175. Similarly, if I want to make this 11 as 0, then I will multiply this 1 by minus 11 and then add it to 11. And similarly this one. So the next step is to make these elements as 0. Okay, and similar row operations, and then these row operations will be adopted. So these are the operations which are adopted on the row, and then we, in the linear algebra, we have already adopted those row operations. So here you can see that this step has been performed. So in the previous step, all this value was 0 already, so there was no need to perform anything over here. This value was 8, this value was 11, this value was minus 175. But after performing those operations, all these values have become 0. And then you can see that other values have also changed, especially the solution value has changed from 0 to 1050. The solution value has changed from 0 to 1050 over here. So this is the first iteration. Okay, this is the first iteration. So after doing this, now we will again look at the this first row. In this first row, so in this first row now we have is minus 150 as the only negative value. So we will perform these operations until all the values in this Z row become positive. But still there is a negative value, which will mean that we still can find the optimum solution over here. Okay, we still need to find. So since this is the only negative value, so this is the most negative value over here. So in our next step, now x1 becomes the what kind of variable? Entering or leaving?
Entering.
Yeah, x1 becomes the entering variable. Okay, so now since it is the entering variable, so now we will take these coefficients. Okay, and then we will take the values of in the solution, starting from the just leave the Z row that is not needed. So we will divide these values of the solution, 11 with the 7. So we'll get this. We will get 32 with 10. We will get this. And then we will get divide 9 with 1. We will get this. And we will get 6 with 0. We will get this. So we will get these new intercept values. So out of these new intercept values, the least positive value is 1.57. Okay, so least positive value is 1.57. So that least positive value of 1.7 will suggest us that S1 will be the what kind of variable in this step?
Leaving.
Leaving variable. So it will be a leaving variable. So then S1 will be replaced by X1 in our next iteration. So that we will do over here. So then in this case, what we can see over here is that it has become X1. Okay, it has become X1. But in the previous step, now I can see that now since it is the leaving variable, so their pivot value, the pivot value over here is 7. Okay, the pivot value over here is 7. So what we have to do is we have to divide this row by 7 throughout. Okay, by this 7 throughout. So 7 divided by 7, 0 divided by 7, 1 divided by 7, and like that. And then we will get like this, these elements. Okay, all the other elements are same as before. We will get these elements. And what will be our next step?
To multiply x1 to 150.
Yes.
Gauss.
So yes, yes, yeah, yeah. So we have to make all the other elements in this column as 0. So for example, 1, we have to make eliminate this 150, and then as 0, and then we have to make this 10 as 0, and then 1 as 0, and this we don't need, this is already a 0. So what we will do is, so 1 will be multiplied by minus 150, 1 will be multiplied by 150 and then added it to minus 150. Okay, so this will make it 0, this will make it 0, this will make it 0. So in the next step, these values will become 0. Okay, these values will become 0. These are by the row operations. Okay, so now after doing this, now again we will look at this first row. Okay, this first row unfortunately has another negative value. Okay, so that means we cannot stop our operations here. So since it is a negative value over here, so this will become the entering variable. Okay, so since this is an entering variable, so now what we have to do is to divide this 1.57, this minus 1.57, so this will be minus 1. Okay, and then 16 with 7, this will be 2.11, and then 7.42 with 1.57, this will be 4.72, and 6 divided by 1, so it will be 6. So we have in the intercept now we have 4 values. One of them is negative, so we will not consider that. The other two values are, the other three values are 2, 4, and 6. So out of this, 2 is the least positive value. Okay, remember that in this case, we will not consider the negative value. We will consider the least positive value. So it will be 2.111. So now since it is 2.111, so corresponding variable over here, S2 will become the leaving variable. So that means S2 will go out, S4 will come in over here. Okay, S4 will come in. Okay, so S2 will go out, S4 will come in. So that is what I have shown over here. Okay, that is what I have shown over here. But remember that since the intersection of S4 and in these two rows, S4 and S2 rows, is 7.71426. So this pivot position is not equal to 1. So what we have to do is we have to divide throughout this row by 7.714286 to make it as 1. So that is what has been done over here. Okay, that is what has been done over here. So to make it as 1. So it will be 2.111, and then earlier this value was 1. So 1 divided by 7.71. So that will be 0.12963. Okay, so this will become 1. And then again, now we have to perform the Gauss-Jordan elimination process to make these elements minus 60, minus 1.57, and 1.57, and this 1 as zeros. Okay, so we have to perform the row operations to make these as zeros. And then after doing this, now let's see what happens. Yeah, so after we have done this, yeah, for these row operations, so we can see that now the first row has no negative value, So first row has no negative value. So when this first row has no negative value, then that means we have achieved the optimal solution. And then we can directly read the optimal solution from this solution column, So the optimum solution is the value of Z is 1413.889. And this value can be obtained at the value of x1 equal to 4.889. Okay, and the value of x2 at 3.8889. With the values of the slack variables S3 and S4 are respectively 4.1 and 2.1 equal to. while the values of the slack variables S1 and S2, because these are not appearing over here, will be 0. That means these constraints are fully utilized, whereas the constraints S3 and S4, that is the storage constraints, have not been fully utilized. So this gives us the solution of the by the simplex method. So we can employ this solution on the Excel. In fact, I have whatever the results which I have obtained over here are obtained from the Excel calculation. So for example, I took this on this over here in Excel. Okay. So repetitively, I performed these operations over here, and then we got these values. So that is the simplex method. So in this simplex method, so you can see that you perform the solutions until that point. Okay, when you get not a negative value of any coefficients in this first Z row. Okay, all the values are positive over here. Do you have any questions up to now?
No questions.
So I hope that it is understandable. So remember that I have done this example purely from the a mathematical algorithm point of view. If you will see this example, the same example has been given in the book, but in the book they have adopted a slightly shorter approach. In that case, they have had only 2 iterations. I had what the way I have shown is like that is involving the 3 iterations, because the book used the graphical group took the help from the graphical solution. So the group in the book, the method used was to move from A to B and then B to C. But the method which I have used is like that. So to move from A to E, then to D to C. But both methods are producing the same results. But of course, the method which is given in the book uses a less number of iterations. However, this method we can only use when we already know the solution. So since in this case, for the illustration purpose, the book just did it like this. So instead of taking the minus 175 as the pivot value, they took the value of minus 150 as the pivot value over here. So which shows that we can change the order of the selection of these entering variable over here. So, but logically speaking, when we are doing the when we are solving any linear programming solutions, we don't have available. We are not available with any graphical solution with us. So we don't have any idea of the solution. So therefore, as an algorithm, we have to go from the least negative value. We have to start from the least negative value. So then we will end up to the solution. But in this case, if we will start from the minus 150, then it will take only 2 steps. Okay, but as an algorithm, we have to start from the least negative, most negative value for the entering variable. Okay? So that is the difference between what I have shown to you and the solution given in the book. Okay, so both are correct, but we will in a standard way we will adopt this solution. Okay, so that is the one. And do you have any question about this? So And this is the solution which is only applicable for the when we want to maximize this function. But you may ask that how about when we want to minimize certain functions? So in those situations, when we want to minimize this function, then we cannot, we can set up the table, of course, we can set it up. But when we want to minimize it, then I think there are certain modifications which we will need to do in those formulations. Which actually are not covered in this book. So rather, I will also not go into the details for the minimizing solution by the simplex method over here. Okay, so therefore, for the constraint optimization, we will only look at the problems which maximize the objective function rather than we look at the minimize the objective function. In fact, in this type of these types of problems, linear programming problems are type of a very large set of problems, which are covered in the um, uh, in the course such as the operations research. Okay, so that is operations research is a separate course in which all the linear programming and all the other programming techniques are considered. So in this course, it is just an introduction to the linear programming method, and to that aspect, the simplex method. Okay, so we cannot do the exact same procedure for the minimizing approach. We may need to do some certain modifications, but of course, these for the minimizing problem has not been covered in this book. So therefore, we will also skip to that. So the purpose is only to give the brief introduction with this simplex method. Okay, so this was the simplex method. So now later on, we will have this topic is almost covered. Then later on in this topic, we have the computer approaches for the optimization. So those computer approaches for the optimization, I will cover in our next class for the lab. Okay. So on Monday, there is a holiday. So we are not meeting on Monday.